Hi, I'm Ray Salemi, the author of the UVM Primer, and this is the second of the code videos that are associated with the UVM Primer. The purpose of these videos is to walk through the code examples so that we don't have to discuss them in detail in the book. The primer itself starts out with a very simple test bench, which is the one we're looking at in this chapter, a single file test bench that handles the TinyALU. And then we're going to take this test bench and over the course of the book turn it into a UVM test bench. The test bench has three parts to it: a tester, a scoreboard that checks to make sure that the TinyALU, which is our device under test, is working properly, and a coverage section to make sure that we've functionally covered everything that we want to functionally cover in the DUT. Right now we're going to start by just looking at the tester. So this is a Verilog test bench, or system Verilog test bench. We can see at the top that we've instantiated the DUT right here, which is the TinyALU DUT. That's a VHDL device under test that does these simple operations: no op, add op, and op, XOR op, mul op, or reset op. And if we look at the previous video, you can see that the operations that we have here in these enumerated types match the bits that are in the actual TinyALU. So it decodes these bits, and you can see, for example, that the multiply operation is the only operation with the third bit set, and that's used to control a mux that's down in the TinyALU. All of that is beneath what we have to look at right now. All we have to see here is that we have a DUT and that we want to drive stimulus into it and make sure that it works properly. If you remember, this DUT has an A and a B bus, a clock, an operation, and then this start and done signal. So we raise the start signal to say we've started an operation, and then we wait for the done signal to go up to say that it's done, and the result goes in result. This is system Verilog, so since my signals at this level are the same names as the signals inside the DUT, I don't need to do anything other than use the port names with dots in front of them to connect them up. Okay, if we go down to the bottom of the file, we see that we've got our tester. And the way the tester works is it drops the reset signal, waits a couple of clocks, and drops the start signal. And now we're ready to do 1,000 operations. And what we do is at the negative edge of each clock, we get an operation, and we get the data for that operation. We raise the start signal. And if we're doing a no op or a reset op, we just drop the start signal again. We don't worry about it. If we do a no op, we wait until the positive edge of the clock, then drop the start signal. But on a reset, we just drop it immediately. Anything else, any of the operations, we wait for the done signal, and when that comes up, then we drop the start signal. And that's the basic operation of the DUT. These methods here, get op and get data, these functions are allowing us to do constrained random. Now, I don't talk about constrained random verification in detail in the UVM primer because that book is focused on the UVM. I do talk about it in my other book called FPGA Simulation, and there we talk about constrained random in more detail. But let's just take a quick look. We want to get an operation, a random operation, and we want to get random data. So if we go up to the getOp function, we see the way the getOp function works is it randomly picks, op choice is a 3-bit number, we randomly fill that 3-bit number, and then based on what we got randomly, we either return a no-op, an add, an and, an XOR, a mul, or no-op, or a reset. In fact, we've got a 50% chance here of getting a no-op or a reset. But this allows us to make sure that all of the results that come out of getOp are legal, because they will always match up to one of these enumerated types. On the getData front, you'll see we use getData to return A and B. We didn't want to simply make A and B random, because then the odds of getting interesting numbers would be very low, right? That's 1 out of 256 chance of getting a 0, for example. 1 out of a 256 chance of getting all 1s. So instead what we do is we took 2 bits and we randomly set those 2 bits. If the 2 bits are both zeros, then we return a 0, so that's a 1/4 chance of getting zeros. If the 2 bits are 1, then we return FF, and so that's a 1/4 chance of getting FF. Otherwise, we return a random 8-bit number. So now we have a constrained random stimulus that's more likely to give us something that's interesting. And so that's what this code is doing here. Now, if we are going to run random stimulus on a DUT, then we need to check to make sure that the DUT is working properly without having to look at waveforms, for example. We have an always block that we call scoreboard that does that for us. So the way the scoreboard block works is it waits for the done signal to go high, and as soon as the done signal goes high, it grabs the operation, and based on the operation, it predicts a result. So if the operation is add op, then we do an add, otherwise an AND, an XOR, or a multiply. And the predicted result comes immediately out of those. And then what we do is, as long as we're not doing a no-op or a reset, we compare the predicted result to the bus that has the result. And if those are different, then we mark that we failed, and we return an error code. So that's the scoreboard. We're going to see different ways of doing the scoreboard as we move forward in the book. Finally, there's coverage. We use functional coverage in this design, as you really should do with constrained random, to make sure that we've covered everything we want. Again, I'm not going to get into cover groups in detail here. Those are covered in FPGA simulation. But at a broad point, we can say we've created these system Verilog cover groups. This one makes sure that we've tested all of the single cycle operations. This makes sure we tested all the multi-cycle operations. This tests that every operation happened before and after a reset. This tests that we had a single operation and then a multiply, and then a multiply and then a single, and that's testing the different directions of the pipelining. We also tested that we had a case where every operation happened twice in a row, and we also tested 3 to 5 multiplies. So that's one cover group. We have another cover group, and this one is discussed in detail in FPGA simulation. This one checks that we've tested all of our operations with all zeros and all ones on the different legs against all the operations. So we can kind of push the boundaries and the edges of the design. We have these 2 cover groups, and what we do with those is we declare variables to hold them, and then at the beginning of our simulation we create these cover groups, and then we have a simple loop that looks and waits for the negative edge of the clock, and then it samples, and it returns and fills in the cover groups as it samples the operations, and it samples the A and the B legs, and make sure that we've tested all the combinations of operations in A and B legs. So this covers the basics of the initial test bench. This test bench is able to, when you run this test bench, you see you completely test the TinyALU. We get all of the operations covered, and we get all the interesting data covered. In our next section, our next video, we're going to look at how to take this single file test bench and start to break it apart, because the problem with this test bench is it's very hard to reuse. I mean, it works for a TinyALU, which is by definition tiny, but we want to make something that will be able to be reused, or techniques that can be used on a much larger design.